Okay, thanks a lot for the organizer for this fantastic opportunity with so many young researchers. So my talk is going to be oriented toward like open problems, since you have many people interested in random walks. This is a model of interacting random walks. So okay, so let me explain the model. It's going to be about internal diffusion limited aggregation. So there is a slow process, diffusion, a fast one, aggregation. And typically that's a famous model when you deal with random walks. I'm going to add something. So there is already a huge amount of models, and I'm introducing a new type of model. And this work is joint with Vittoria Silvestri and Lorenzo Taggi in Rome. Okay, so let me start with a model. The model of, I will just call it IDLA with a simple random walk. Let's start with that. So what's a simple random walk on the lattice? And you'll see my interpretation is a little bit different. I try to give like a moral interpretation in all the models. So I am on a side of the lattice. And next step, imagine it's in discrete time. This individual gives rise to a child, just one, and dies. So it's strange to present random walk like that, but disappear. And you keep on doing that. So this jump, it produced one kid, and the kid jumped to one of the nearest neighbor uniformly at random. Okay, so if you want, the only kid moved away from the house, and in a uniformly random nearest neighbor side. Okay, that's for simple random walk. Now what's IDLA? So that's my explored region. So you need, let me call it D. That's a distinguished site, the origin. And I'm assuming that I've already explored this region. This is explored. So in the sense of, on each side of this region, there is a settler, someone who has settled. You send your random walk from the origin, and it roams until you hit the boundary of this region. So it can take a long time. So if I do a real simulation, you know that it takes a huge amount of time. Let's say diameter, let's say distance square. You went there, and you say, I'm establishing myself in this region. That's the place where I settle the first free space. This was completely explored. Now, the new region, if you want, is and Z belong to the boundary of D, okay? And the law of Z is the first exit law of a simple random walk from this domain. So I have increased, I've increased the boundary with the harmonic measure seen from the origin. That's the way, that's the law in which I choose to increase the domain. That's internal DLA with simple random walks. You keep on adding particles. So, and let me give a notation. The aggregate, because it's an aggregation, and you see that right away when I found the first free site, I immediately settled. So that's why that's fast. This is fast, and this is slow. It took a lot of time to explore. And the aggregate here, when I send n random walk, my initial configuration is n time, they all start at 0. And S is for settle. So I'm settlement, to settle. The settlement of all these explorers. So, okay, so it's a model of colonization. How do you colonize space? You add people, and you want to know what's the shape of the explored region. Okay? That's the model. So it's pretty simple. You could, well, so to let you some time to digest the model, maybe I tell you about its history. So it was introduced in math in '91 by Diaconis and Fulton. And it was introduced 5 years before in the physical chemistry community by Mikin and Deutsch for a model of erosion. So for chemists, this is a model of erosion. Some particle eats some material in the boundary. And it was a real model of erosion, but so 86 for chemists. But the point of view of Diaconis and Fulton was more like about to have something which would be abelian. So they stressed the word abelian. In the sense that no matter how you send your particle, no matter where you stop one and start another one and start it again, it will produce statistically the same cluster. So they had this word was important in their paper, and we will see some. Now it's too simple, but we will see what it means. Okay. And just 1 year later, Lawler, Bramson, and Griffith produced the shape theorem. That is, they showed that the asymptotic shape is a Euclidean ball. So that's ball. So let me call it the Euclidean ball of radius r. I call it BR. And so their statement is that the cluster or the aggregate, when you send an amount of particle which would be the same volume as the sphere of radius n, you send them at 0, and so they are basically very close to a ball of radius, let's say 1 minus epsilon n, and the same thing with the 1 plus epsilon here. And the probability that this happens goes to 1 for any epsilon. So as n goes to infinity, so you fix epsilon. And so the shape of the aggregate is basically a Euclidean ball. Okay? And that's really what we want to understand, especially why it's Euclidean. And we also know that this model has very small fluctuation. So it was obtained 30 years later, around 2010, that the fluctuation are logarithmic. The worst, so that's one of the worst for fluctuation. Logarithmic in dimension 2, and sublogarithmic in dimension 3 and more. Okay. So, is the model clear to everyone of you? That's let's go to introduce the model I'm interested in, branching random walk. So what is a branching random walk? Same picture, but now the parent is more ambitious. He does not just have one kid, he has certain number of kids, k kids. And each one independently choose one of a nearest neighbor uniformly at random. The first one goes there, second one there, third one here. Okay, in my case, k equals 3. But what you do each step, each individual draws, you draw a certain number of children according to a law, the offspring distribution. And this parent is ambitious only well, he's not so ambitious because he still wants, on the average, to just have one kid. So it's a critical branching process. So it means one kid on average. Okay, and each kid does the same thing independently, and you keep on growing. That's branching random walk. Okay, and indeed, I'm not saying, but you need the variance to exist. I even need some small exponential moment on nu. That's my hypothesis. What else? Maybe to make it different from, if nu is concentrated on 1, then that's the simple random walk. So I want nu of 1 to be different, from 1. And what you know from, the population is a Bien-Aimé Galton-Watson tree, critical. So you know that typically it's a finite tree that you get. Okay? And then what's internal DLA made of that? So you have the explored region, which I draw white. Let me call it D. A distinguished point. And you send random, this branching random walk. First simulation, they died, all died here. No chance, no one made it up to the boundary, so you don't see anything. Doesn't grow. Send a second one. It was went farther, but still not enough. It died here. So you change color. So you have to try a lot of simulations to see one of them arriving to the boundary. And when it does, it brings a lot of people. So I'm on top of them. And so you stop them on the boundary, and if there is a place where many of them have piled up, you send them again. So in one launch, the boundary, the cluster is going to increase a lot, not just by one. Most of the time it does not change. But if you make it to the boundary, then you come with a population, let me call it eta of the boundary. You keep the first two arriving there, they settle. So how much you keep? You keep this amount, the support of this. This is kept. You keep this amount of settlers. And the one on top of them, the excess settlers, you send them to explore new region. Okay? So it's a, yes?
And do they keep branching?
And they keep branching. And they keep branching. The mechanism of this diffusion now is a branching diffusion. And the aggregation is first, you could give exponential clocks to the particle, and therefore you know which one rings first, and you send them. So this process of stabilizing branching random walk is well defined because the tree is finite. And there is this abelian property that which says that in this model, if you want to know the cluster and its statistical properties, it's not important in which order you do the stabilization. Okay, so that's important is that the model is well defined. It's well defined because the order you choose is irrelevant. Okay.
One more question?
Yes.
If when one particle hits the boundary,
yes,
it settles, and maybe there's more that have to go on from there, but there's another particle still alive inside the interior.
Yes.
Does that one continue also to evolve until it either dies out or gets bound?
Yes. I mean, so an individual will die when he gives birth to kids, and unless you arrive in a settling position, and in which case he settles, he stays there. He built a home and he's there. So what do I? Okay, so the first thing maybe is to get some intuition about okay, that's the two model I'm going to look at. Okay, before going to some intuition, I want to say why we were led to look at this other model, branching random walk. Is it just to have one more model, write one more paper? And actually not. It was because the physics is different. But so how we understood that the physics was going to be different. Of aggregation. So there was in the community some questions about why you get an Euclidean ball. Can you find another model which would give rise to another type of ball, not L2 but another type of balls? And Gadi Kozma was behind this type of ideas to find to interpolate between different type of models. So let me just mention that if you start from your distinguished site to be far away at infinity, if the distinguished site where you throw all your particle is, let's say, at infinity, and you have to condition the walk to hit the boundary of your cluster, then what you grow is not at all a ball, it's rather something with long fingers. So it's a type of ramified fractal, long fingers. So here I'm growing the boundary with respect to the harmonic measure seen from infinity, and the phenomenology is completely different. So it's long fingers, and the model is so hard that there is no paper on it. Since maybe 86, with just only bold person was Castan, I would say, but no one has shown some reinforcement of the fingers. There's not a bound saying the fingers are larger than n to the 1 over d, better than a ball. So that's open. And then there was another proposition. There is a model called Eden model where you send particle uniformly on the boundary. And there also, I don't know about written results, but you don't expect a sphere, flat faces. So there is Eden model where you add a site uniformly on the boundary. So you grow it uniformly. Let's say no result, except Kesten. There is an unpublished paper of Kesten. But then there is one thing, a nice model called uniform. internal DLA. And there, what you do is that the distinguished site is chosen uniformly at random inside the cluster. So you built a region. I mean, this is the explored region, your cluster, and you choose to throw the new particle uniformly inside the domain. But there, still, the shape is spherical. Euclidean is a ball. So uniform internal DLA means in the distinguished site, you launch simple random walk uniformly from the domain. And so it's there is Cyril Lucas was behind this model, and his friends. There is Hugo Duminil-Copin, there is Cosma, there is Yaddin. So there is a group of friends, but it's a ball. No luck, it's again a ball. Here, I know that the fluctuations are logarithmic. You expect here the fluctuation in the uniform case to be a polynomial, but there is no study of the fluctuations. So fluctuations are open. Let me. Oh. Okay. Okay. Still another model for and finally, I want to mention activated random walks as a big family of models where the particle does not aggregate right away. It has some time, so there is an exponential parameter of rate lambda, and the particle, each simple random walk roams, even if it's outside the explored region, and when the time mark, when there is a time mark, he flashes and he looks at his environment. If it's empty, he settles. Otherwise, if there is someone, he moves. And the thing is that if someone else comes on a settler, he wakes it up. So it's a model where the case lambda equal infinity, you settle right away, correspond to internal DLA. And this model is much richer because you can choose the initial condition also. Internal DLA, the initial condition is this one. Whereas here, typically, people are interested in having a product measure of a given density and checking if there is total settlement or not. Okay, well, you can add branching, and it makes a whole class of new models. Maybe with new physics, but they're studying settlement activation might be interesting. So if you are idle, you can think, let's add branching random walk to activated random walk and look at the phase diagram. That's a possible big source of problems. Okay. Now, a little bit of intuition so as to appreciate, to see what's happening for the shape theorem of branching random walk internal DLA. Some intuition. So everybody knows that simple random walk need a very long time this is R. So you go out of it in a time R square. So the walk at time R square typically is on the boundary of this ball. And we saw with a few simulations I wrote on the branching random walk that most of the time you don't reach. So it's a rare event to reach the boundary. And so what's the chance? What's the chance you reach the boundary? And I want to do it in a wrong way, to give the correct answer in a wrong way. But to use Perla's talk. Because she said, okay, for branching random walk, if you want to hit something, you look at what is called the capacity of this, let's say, the boundary of this ball, and you divide by the distance to the power d minus 2. So this was her message for a critical branching tree. And what's the branching capacity of a ball of the boundary or a ball of radius r? It's r to the d minus 4. This is r to the d minus 2, and so you have 1 over r squared. This is also the 1 arm exponent for critical percolation, and this is a null result of, I have to say, it's almost like if you ask a population for a Galton-Watson tree to survive a time r squared. Because you need that the population survives the time r squared so that one of them, who is just a trajectory of length r squared, hit the boundary. So it's as if on a Galton-Watson tree, I'm asking what's the chance that z r squared be positive. And this is like 1 over r squared. And this is an old result of Yaglom in the 40s or 45. Okay. So you know that it's very hard to reach the boundary. On the other hand, you can ask yourself how many particles, what's the expected number of particles reaching the boundary? And this is my notation for the pioneers. The pioneers in a colonization process are the first person arriving in some region and saying, that's mine. Okay, so what does it mean? That's all the individuals such that S of u belong to the boundary, but all their ancestors do not. So they are inside. And this is, let's say, the external boundary. So this is the set of pioneers. And this is eta, it's a set of, it's not individuals, but it's positions. That's the position of some individuals of my tree, such that their position is on BR, but their ancestors are inside the ball. And if you want to have their number when you start particle at 0, you say, okay, I'm going to count how many pioneers in generation n. I know that it's a critical tree, so on the average I have 1 person per generation. So I have this, and you count how many u's in Zn, such that I have this thing. S of u belong to the boundary, and S of v does not. All their ancestors are inside. And what you find, since Zn has a size 1 on the expectation, you find when you sum over n, the probability that a simple random walk hits, starting at 0, hits the boundary. So it's 1. If I'm inside, the exact expected number of person arriving is 1. Just like a simple random walk, just one guy arrives, if you want. And that's an equality. And this gives me that the expected number of people arriving knowing that I touch the boundary, knowing that 0 is connected with the boundary, is, sometimes I use that but to say just a simple random walk has hit the boundary, is just the ratio of 1 over the probability to reach. So I'm arriving with r squared sites. So it means that when you do this event, you arrive with a huge amount of sides. If you make the event, so that this times the chance to hit is exactly 1. Okay, so now that's the physics of the game. Because now let's do some internal DLA. Imagine I have a shape like that, almost a ball. You send branching random walk, most of them die, until the first one, the one who is going to grow the cluster, is one who touches the boundary. And it touches the boundary of this almost ball of radius r with r square side. So you have, let's say, in dimension 2, this is the boundaries of order of side r, if you want, and this is r squared, so they will be on top of each other a lot. This is a huge amount of particles that have stopped on the boundary just before releasing them. But what you see is that this r squared here, if it's larger than the boundary itself, you might have problems, because with a positive probability, they might all escape in one quadrant, for example. And then when you release them, r squared is enough to make it's of the same order as the ball itself, the ball that they were. So with this physics in mind, you might say, okay, this will imply if this number of stopped particle, and usually with a positive probability, they might clump together, which means that with a positive probability, the next step is not going to be close to a ball. Okay? No shape theorem. So you expect that there is no shape theorem. If 2 is larger than this, and you expect that if 2 is less than d minus 1, then shape theorem. And so usually when you're a physicist, you even know that beforehand, that even at dimension 3, which is critical, you will have a shape theorem. You will have a shape theorem and some logarithmic error. Okay. So that's what this is how, this is what Lorenzo told me just after a talk on branching random walk. He said, we should do that because there is a phase transition in dimension. And I said, come on, it's not possible. It's a model of erosion. And then, so we had this goal. Let's show there is no shape theorem in dimension 2. So we made simulation. Let me draw you some simulation. So in dimension 2, you have an explored region. It's hard to make simulation with this model. I mean, they suffered. I have a physicist friend, Emilio Cirillo, who suffered a lot too. But what you see, next step is that. And then you see some petals. Then a big one. And then big one, things like that. So, and the petals are of the same volume as the initial, the previous cluster, something like that. So it was clear that there was no spherical shape theorem. So results, just once you know what you want to show, it was easy to see that result in d equal 1 and 2, no shape theorem. So I know that Jonathan is going to tell me in dimension 1 it's an interval, so there is a shape. But the center is, keeps moving. Makes big moves. So no shape theorem means centered shape theorem, and we are not, this is a lie because we cannot get it really. I would say no spherical no Euclidean ball can be a shape, and we believe there is no shape theorem. And a nice open problem would be to describe the growth of this, or a way to describe a macroscopic growth of this flower. It grows like a flower by petals. So we don't have an idea of how to make a dynamics, continuous dynamics, which would reproduce that. But so so what do I mean? To be a little bit more precise, let's this be all the shapes which looks like balls.
Can you describe the fluctuations in dimension 1?
Dimension 1. We did not do it. No. If you know activated random walks and loose models, even dimension 1 is not obvious. But that's maybe, I mean, I think you can handle it, dimension 1. Yeah. Dimension 2 is already, so let me describe. Those are the shape, such that you can put a ball inside. Something like that. There is a T, there exists some radius, well, the volume of A such that that it's inside two balls. That's the spherical Euclidean shape, space of shape. And what you can show is that in dimension 2, my settlement, when I start with an n particle at 0, infinitely often goes out of this spherical. But open problem, nice open problem, is to show, so I'm going out of any spherical shape. If I start with one which is almost spherical, I can show you the positive probability I go out. What's open is still, even if it's a flower, you should be able to see that a small ball is inside. And if I send this amount, you cannot show that a small ball of radius alpha n, no, so I have to send something which will fill a ball, radius n square, let's say, with a positive probability as alpha goes to 1, let's say, alpha going to 0, sorry, and n go to infinity, show that in dimension 2, your aggregate contains a very small ball, probability going to 1. Cannot do that. So if I could start with that, I could maybe do something better, to have no shape at all. Maybe convex shapes we can show there is no convex shape, but okay, that's not. On the other hand, when D is larger than 2, then you know that eventually you enter this space. You have a shape theorem. That is the probability that your cluster belong to the, eventually for n large, eventually in n is 1. And you have bound on the fluctuation. There you have bound. You expect the fluctuation to be polynomial, and you have some bound. So we know in this case that fluctuations are, okay, let me maybe mention it. We have polynomial bound on the worst fluctuation. Maybe it's easier to erase this flower. So I want to try this thing. Okay, it was easy. in dimension bigger than 2, you have something called the outer error and the inner error, the inner bound, when you send in the sense that your aggregate is how many particles? An amount which would fill a ball of radius n, started at 0, and this is always, you can find the worst possible, the longest possible finger, and the deepest hole. And what you can show is that the probability that those are big, or this one is big, I forgot I think something like that, but I'm not sure, infinitely often with probability 0, sorry. So it means that I cannot have an inner and outer bound which go beyond some polynomial thing infinitely often. Means I have a way, I have polynomial bounds, open problem, get the optimal one. I believe it's not 1/2 here. Optimal one. Okay, and I mean, usually I want to show, I'm going to do like Orion, I'm not going to show the most original part, but maybe tell you that there are some nice problems. A nice problem is to do your internal DLA with a subcritical trees, okay? To find some new physics. Subcritical trees. What would it bring you? In dimension, in any dimension, start with dimension 3. So something that to reach radius n costs an exponential time, an exponential in n. And so the one who is going to make it is going to be ballistic. He doesn't want to waste time. And so what we expect is to have a ball like that in L1. So it's not going to be the Euclidean ball. Euclidean is linked with the diffusion. If it's diffusion, is chance that it's Euclidean. If it's ballistic, you want to have all the points which are the same graph distance. So you expect this L1 norm. We don't know it, so it's open. But it goes in the questions that Gadi Kozma asked, how to find new shapes. That's okay. So let me still tell you the way we deal with the branching, because the new thing here is branching, and what I've tried to explain is that the problem that we face is that fingers can be long because your cousin, your siblings made the way to you. They paved the way and you could go far. And usually in simple random walk, you send one after the other one, they all start from 0. Whereas here, the siblings start along the path. They might be close to you, and they might use you to go farther. Okay, so how do we deal with that? Okay, let me maybe write here. I'm sure I forgot an open problem, because I had so many open problems. Let me check. Okay, I think I went fast, but I gave them all. Okay.
mean, I have a question. With this last problem with the subcritical trees, why do you have d bigger than or equal to 3 there? Why not d equals 2?
Yeah, I think that they're equal to, because it's true that here when you get there, you are alone. You are basically, there is a few ones. You don't have n squared. So the number of particles you get there is 1. Therefore, yes. Yes. Good. Okay. So let me tell you what's the proof of all that. So the first paper of Lawler, Bramson, and Griffith proposed like a general approach. So let me call it just Lawler's approach, but it's these 3 guys, where you first obtain the inner bound. That is, you show that you are going to cover a large region. So it's like a covering. You want to show that you can cover a large region. Large in the sense of the smallest possible inner error. And so with the excess particle, because what you send is enough to fill a ball, that's your initial configuration, show first that you fill a big ball. Now, with the excess particle that you are going to stop on this boundary, that they are stopped on the boundary of Pn, you have a small amount if delta is good, if delta I is good. So you have first to work hard on the inner bound. If delta I is large, small, sorry. Those particles, you have to explain why they cannot make long finger. Why you cannot have long finger. And the idea of these 3 guys is pretty simple. If you want to go far away, you have to hit an explored region close to it. So the main thing is to obtain the probability to hit a region is something, a spherical part of a region is something well known. It's about the region over basically the distance to the d minus 1. So these are bounds that those guys knew or even discovered. And so, and therefore, to go far away, you're bounded by the size of the explored region also close to the place you want to be. So in a sense, the increase in the, if mu L is the number, the average number of particles at a distance k when I send L of them, if you want the Lth one to stop on the kth, let's say the kth shell, you see that this is going to be bounded by the probability to hit the explored region on when you send L-1 particle on K-1. So they have a type of branching multi-type bound in which they control the rate at which the explored region grows shell by shell. So to go far away, you have to cross the explored region. And this simple idea cannot work in our case. So the original part really is the outer bound. In which, let's say, there is 4 ingredients. I think I have like 1 or 2 minutes? Or 1 or 2 minutes. Okay. So the first ingredient is that we introduce a process which is much simpler to handle, a process which settles less. So if you settle or if you slip less, you agree that maybe you can go farther or work more. So the first thing is to have a process which go farther away, slip less than our process. And that's a process where I'm going to only probe the environment at a random surface. I have to choose it correctly so that so I choose a random surface at which I probe the thing, and this works. I can compare the two processes because there is something here called the least action principle. That is a process which is fast, which sleeps less, create more activity. It's not completely obvious because in the branching case, if you don't settle, you can have kits, but they can evaporate. So it doesn't mean that the aggregate is larger. You can explode, you can evaporate. So it's not the configuration which is coupled. It's the local time, in a sense. It's the odometer. There is something called odometer, so we couple the odometer. And this process is much simpler because I'm just asking at what's happening if I flash on a given place. I have good green function estimate on the boundary of a sphere, and I have two types of particles. The one who are going to flash on an explored region, and the one who are going to flash on a cousin. And I have to treat the one who flashed on the cousin, and this is about comparing the pioneers with their range. So I want to compare this with what I call the range of the... I want to show that the number excess settlers is small. And this is basically, if I can compare the second moment of this to the first moment, that's the number, that's the support, and what I show is that this is small. And there is a way to go from the kind of square, there is no parenthesis, square of the number of pioneers minus their mean to this number. This is second moment computation of the local time. We know how to do them. So that's how we control the excess particle. And then we choose kind of, this is also random, such that you have a contraction. The number of particles who dies or who do not settle, or no, who settle, is a fraction of the total number. So we have to choose the geometry in function of the number of particles arriving to get a few steps of contraction, and then we are done. That's basically the techniques for the outer bound and the model. Thanks a lot.